Heat's been working in waste innovation for many, many years. It handles all the waste out of jet, and we've used that experience to develop new ways to detritiate hard waste. And getting the tritium out of hard waste is fantastic because we actually recover the fuel as well as making the waste lower activity. Over the years, we've been supporting the ITER program as well and helping them understand their strategies for dealing with tritiated waste. And that's a very important part of their dialogue with their regulator to show that they have mechanisms and strategies for dealing with their tritiated waste. So JDR is another fantastic opportunity for us to develop new processes, new technologies, new strategies to deal with tritiated waste. We'll be using JET to drive that innovation and to understand the costs better.
With JDR and the decommissioning of the tokamak, we have a once-in-a-lifetime opportunity to take materials directly from the first wall of a device which has seen live plasma and tritiated plasma. The idea is to have a look at those tiles in an archaeological way almost, removed from the tokamak in a way where we can derive information from the geographic positioning of the tiles and look at those properties that result from exposure to plasma to give us an understanding of how plasmas impact materials and damage them. We can also validate some of the activation of the materials, which we've previously calculated using some of our very world-class inventory code, FISPACT, to check whether those degrees of activation materialize. And then thirdly, to look at the tritium that has been retained and permeated into the materials. Those are three major avenues of material science work enabled through JDR. And from that come samples which can continue to be used, and we hope to put those into a national archive, which would underpin materials research in nuclear engineering and in fusion material science for a decade or more to come. The JDR post-mortem, we're calling it, of materials allows us to strengthen relationships with both types of sector in materials research. Industrial sector, the commercial fusion builders of the future who want to understand some of the materials implications for decommissioning, and also the academic community who are doing cutting-edge science in materials interfacing with plasmas in fusion devices.
Generally speaking, I think it's also quite exciting to see what's inside JET. I mean, after all these years of plasma exposure, understanding how the surfaces have changed, how they've been modified, this is a direct interaction between plasmas and walls. So it's actually quite interesting also for plasma physicists to learn that, because this knowledge can also allow us to do better modeling, understand better how the plasma itself behaves. So it's a quite interesting project that has many repercussions. And also, again, the fact that we have this huge fleet of buildings in Calum that will be repurposed will have benefits for many, hopefully also for plasma physicists.